Hi everyone. My name is Marques Cavalcante. I'm from the Federal University of Alagoas in Brazil. And first of all, I would like to thank the organizer, especially my colleague, Julie, for the kind invitation to deliver this talk here. Thank you very much. I will talk about lower bounds for the stability index of constant mean curvature surface. And the results I will present in this talk are part of two joint works with my colleague, Darlane Oliveira, from the State University of Feira de Santana in Bahia, Brazil. We start fixing some notations and present some definitions. We'll denote by M bar our ambient space, which in general is a complete oriented Riemannian manifold of dimension, say, n plus 1. But especially in our theorems, it will be just the Euclidean tree space or the unit tree sphere. In this ambient space, we consider a compact orientable immersed hypersurface. We denote by M. And here could be, this hypersurface could be with boundary or without boundary. And this setting, we can choose a unit normal vector field defined globally on M and denote by A the second fundamental form with respect to this vector field N. Now, if given a smooth function on your hypersurface with compact support, we can construct a variation of our hypersurface M by considering the flow of the vector field U times N, for like something like that. Okay, so for each smooth function with compact support, we can construct a variation of our original hypersurface. Note that under our conditions here, all hypersurface are compact. So in particular, the area is well defined. We denote the area by A, which depends on U and T. Okay. But if U is fixed, we look the area as a function on the parameter of the variation, which here is denoted by T. And so as a function on an interval, we can compute the derivative at t equals to 0, and it's the so-called the first variation formula for the area functional, and you can see that the derivative equals to minus n times the integral of u, the function which generates the variation, times the the mean curvature of your original hypersurface. Well, this is very classical, and we recall that from the first variational formula, we conclude that the well-known variational characterization of minimal and constant mean curvature hypersurface, because of course, if this derivative of the area is 0 for all function u, of course we conclude that the mean curvature is 0. I say m is minimal. And same way, if the derivative is 0 for all functions such that the integral of such function is 0, we conclude that in this case the mean curvature is constant and no 0. This space is very special in this talk, and we denote the space of a smooth function with compact support such that the integral is 0 by f. From the geometric point of view, the variations where the function lies in this space correspond for those variations which preserves the enclosed volume. Okay. Now, at a critical point, I mean, at a minimal hypersurface or at a constant mean curvature hypersurface, when you compute the second derivative of the area functional, again, at t equals to 0, we found a quadratic form. The second derivative is given by this quadratic form here, which involves the gradient of u, the ridge curvature of the ambient space in the direction of the unit normal vector field n, and the norm of the second fundamental form. And of course, integrating by parts, we can rewrite this quadratic form as minus integral of u, j of u, where j is the so-called Jacobi operator of M. It's the Laplacian plus the ridge curvature plus the square norm of A. So in the case, if M is a minimal hypersurface, we define the stability index of M as the maximal dimension of a vector subspace of C infinity 0, where this quadratic form is negatively defined. And of course, not that since the Jacobi operator has a discrete sequence of eigenvalues and the corresponding eigenfunction solve this Dirichlet problem, we can see that the index of a minimal hypersurface is in fact the number of negative eigenvalues of J counted with multiplicity. In the case of constant mean curvature hypersurface, we call the weak stability index. And we define it the same way as the maximum dimension of a vector subspace, but now of F, the space of admissible variations. So the maximum subspace of F, where again, the quadratic form is negatively defined. In this case, we denote this number, the index, as by ind with double fm, the weak index. Well, now when we restrict this quadratic form to the space F, we find a new associative operator, which is denoted by L. And it can be shown, for instance, you can find in a paper of Barbosa and Berra that this operator L is in fact the Jacobi operator minus this functional psi, which is defined by this, like a normalization here. Okay, so but since we now have a new associative operator, and again can see that the weak index of a CMC hypersurface is again the number of negative eigenvalues of this operator L. In both cases, I mean the minimal case and CMC case, the index indicates the number of directions whose variations decrease the area. It's more or less simple to see because once you have a negative eigenvalue from this quadratic form, from the second derivative, and you choose the corresponding eigenfunction to construct your variation, what to have a critical point, and the second derivative is effectively negative. So the area decreases. Okay, so the number of directions in the space of variations where the area decreases the geometric meaning of the index of even in a minimal surface or in a CMC surface. The case of the hypersurface has index 0 is very special. In this case, we see that M is stable. Your minimal surface is stable. In the case of weak index 0, we say that is also stable. And the general fact is that the stability index is strongly related with the topology of the hypersurface. And I try to show this general fact by some null results, some conjectures, and also by our results. Well, it's important to especially for examples, to define, we can define also the index in the case of non-compact minimal or CMC surfaces. And it is defined taking an exhaustion of your hypersurface by compacts. You compute the index on each compact, and then you take the limit. And it's simple to see that this number, the index of this non-compact hypersurface, is well defined. I mean, do not depend on the exhaustion you choose. Of course, in this case, we can have some examples of hypersurface where the index is plus infinite. Let me show and talk about some examples. Of the most simple example, of course, is the hyperplane in the Euclidean space is, of course, a stable minimal hypersurface. And in fact, you have this nice theorem due to Ducarme-Peng, Fischer-Kolber chain, and the pure-water law independently. They show that in the two-dimensional case, I mean, a complete stable minimal surface in A3 is in fact a plane. Note that minimal graphs in the Euclidean space are stable. And so this theorem can be seen as a generalization of the famous Bernstein theorem. And we know from the Bernstein theorem that in higher dimensions, when the main space is at least R8, there are some complete minimal graphs which are not hyperplanes. So in particular, they are stable. And in lower dimensions, complete minimal graphs are hyperplanes. But we don't know what happens about a stable minimal hypersurface in this range of dimensions. And this is a very hard conjecture, actually. The conjecture says that a complete stable minimal hypersurface in Euclidean space, when the dimension is in this between 3 and 6, is in fact a hyperplane. So again, the solution of the Bernstein problem says that it's false in higher dimension. There are other examples. In dimension 2, we have this theorem here, show that this is true, and we don't know in this between 3 and 6, actually. And the next simple example is the catenoid in A3, and the index of the catenoid is 1. The other example is the Enneper surface. There's also a minimal hypersurface in Euclidean space with index 1. And I'd like to mention this theorem due to Lobs and Haas that classify all complete index 1 minimal surface in A3 is either the catenoid or an Enneper surface. Very nice theorem. And the Helicoid actually has index plus infinite, and it's an exercise to see that any periodic minimal surface, which is not a plane, has index plus infinite. Okay. The famous Costa minimal surface has index 5. It was computed in a work of Nayatani. Just recall here this famous minimal surface in A3 has index 5. And some results, classical results, this theorem, nice theorem due to Fischer-Kolber and Gulliver, independently again. They prove that if the ambient space is a three-dimensional complete Riemannian manifold with a non-negative scalar curvature, and if M is a complete oriented minimal surface in M bar with finite index, then In fact, M is conformally diffeomorphic to a compact Riemann surface with a finite number of points removed. In the case of the ambient spaces R3, they prove that it's in fact equivalent. And the minimal surface, a complete minimal surface, has finite index if and only if the total curvature in this sense here is finite, or is equivalent also to say that M is conformally diffeomorphic to a compact Riemann surface with a finite number of points removed. And summarizing, we can say that in the Euclidean 3 space, finite index is equivalent to finite topology. This sense. Now, then, for instance, we conclude that the family of Costa-Hoffman mixed surface, in particular, have each surface in this family has finite index. And I'd like to mention some results that improved these previous results. For instance, this theorem of Antonio Ross. He proved that if M is a complete minimal surface of finite index in R3, then the index is bounded from below by 2G over 3, where G is the genus of the compactification of M. And same year, Grigorian, Netruzov, and Yao found a lower bound for the index by the number of ends. The index of a complete minimal surface in A3 is bounded from below by k minus 1, where k is the number of ends, but this term holds just for embedded minimal surfaces. And more recently, Chodosh and Massimo found this lower bound for the index, again for minimal surface in R3, which involves both the genus and the number of ends, and they improved these lower bounds, and this is the best lower bound we have for minimal surface in R3. It's 1 over 3 times 2G plus 4K minus 5. In the first paper, using these first lower bounds, actually they found a very nice application, because they conclude that there is no complete minimal surface in R3 with index 2, so, as an application to this formula here, it's lower bounds. And I'd like to mention some results in other ambient spaces. For instance, do Carmen da Silveira prove a theorem equivalent to the theorem of Fischer-Kolb and Gulliver for the case of a CMC surface in the hyperbolic space here, H3, with mean curvature equals to 1. So in this case, CMC 1 surface in R3, in fact, share many. We know that this kind of surface, some people call a bright surface, shares many properties as a minimal surface in R3. And so they prove actually that in this case, the surface has finite weak index if and only if the total curvature is finite, in the sense that the integral of the Gaussian curvature is finite. And I'd like to mention this theorem we obtained with Pierre Berrat and Philippe Castillon, where we consider the case of complete minimal surface in H2 cross R with finite total curvature. In this case, we prove that this surface has, in fact, finite index. So we found one direction of the theorems. More results in other space. Now in the case of spheres, I like to recall this theorem of Urbano. He proved that if M is a compact, here compact without boundary, non-totally geodesic surface in the unit 3 sphere, sorry, then the index is at least 5. And if it's 5, it's in fact isometric to a Clifford torus. Very nice theorem. This theorem was generalized for higher dimensions by El-Soufi, and he found a lower bound for the index of, again, compact, non-totally geodesic minimal hypersurface in the unit sphere, SN plus 1. The index is at least n plus 3. Of course, it is the right number we hope to have in higher dimension, but until now, it's an open problem to check what about what happens in the case of equality in higher dimensions. And is in fact a conjecture. We hope that if a minimal hypersurface, compact minimal hypersurface in the unit sphere has index n plus 3, then M is in fact a generalized Clifford torus. So nice conjecture. Brazil and Perdomo considered the case of CMC hypersurface in the unit sphere. And they proved that if M is compact, but not non-totally umbilical, then the weak index is at least n plus 1. And in other results, by Alias, Brazil, and Perdomo, they consider the case of CMC surface, but now with constant scalar curvature. And in this case, they prove that the index is greater than or equal n plus 2, and this number is special because the equality case holds if and only if M is a Clifford torus. And the problem here, the conjecture here, is to prove this theorem, but with no assumptions on the scalar curvature. I mean, if H is constant and the index is n plus 2, then M is a generalized H Clifford torus. Now I'd like to recall this theorem due to Alessandro Savo, where he proved that if M is a compact minimal surface in the unit 3 sphere, then the index is bounded from below by G over 2 plus 4, where G is the genus of this surface, compact, again, without boundary. And also, in higher dimensions, he proved that the index is bounded from below by the first best number over this combinatorial number plus n plus 2. And these results of Savo are key results in this talk and in our theorems. Actually, there is a conjecture due to Marques-Neves related to this theorem, which says that if the ambient space is a Riemannian manifold with positive ridge curvature, then there exists a constant which depends only on the ambient space, only on m bar, such that the index of any compact minimal hypersurface immersed in m bar is bounded from below by this constant times the first best number of m. This conjecture is open in the general case, but it was confirmed by a wide class of ambient manifolds by the works of Ambrosio, Carlotto, Sharp, Mendes, Hadesh, and Gorodsky, Mendes, and Hadesh. There is also what we say the strong version of this conjecture, which says that in fact the index could be bounded from below by a constant times the sum of all bad numbers of your hypersurface. And recently, Antoine Song proved that this estimate holds when the constant depends linearly on the area of M. Very, very nice theorem in the direction of this conjecture. Now I'd like to mention some examples and results for in the CMC case. Of course, geodesic spheres in space forms are stable CMC surface, stable in the sense that the weak index is 0. And in fact, this theorem due to Barbosa, do Carmo, and Schamburg says that only geodesic spheres are CMC stable surface, hypersurface. And so we know that subbubbles are Brown spheres. Okay. The next example of CMC surface in R3 are the Wendt torus, which are topological torus, but of course not embedded from the Alexandrov theorem. And there are families of these torus. I'd like to mention here that Lima, Souza Neto, and Hosman estimated the index of such family of CMC torus, and they proved that the index is at least 8. Of course, as I already mentioned, there are CMC Clifford torus in F3, and the index is 4. And there are many other compact CMC surface of any genus, either in the Euclidean 3 space, as we can see in the works of Capulet, or in the unity sphere, as you can see in the works of Butcher and Paccard. So for any genus, there are CMC surfaces either in R3 or in F3. Okay, but the index are not null, and our results runs in these directions. Like to state our first result, we proved that if M is a compact CMC surface without boundary, if genus G immersed in the Euclidean 3 space, then we prove that the index, the weak index, is bounded from below by G over 3. And in the case of CMC surface in F3, we prove that the index, the weak index, is bounded from below by G over 4. And to prove that, we apply especially the ideas of Antonio Ross and Alessandro Salvo. As a consequence, direct consequence from our theorems, we conclude that in R3 or in F3, there are compact CMC surface with arbitrarily large index, of course, because we know there are CMC surface with arbitrary genus is a consequence of these theorems.